All right, today we're talking about something weird. We're diving into manganese heptoxide, a chemical that is so incredibly unstable, it basically acts like it hates itself and doesn't even want to exist.
And this quote, man, it just nails it. This isn't just some boring substance in a lab. You can almost think of it as a molecule with a personality. And its personality is that it's constantly on the verge of a breakdown, just looking for any excuse to fall apart.
Okay, so what is this stuff? And how in the world do we even make something that so desperately wants to be anything else? Let's get into it. So, this chemical has actually been known about for a while, since the mid-1800s. It shows up as this dark green oily liquid, and its main claim to fame is that it's an incredibly powerful oxidizer. That just means it's extremely good at ripping electrons away from other things, which, as you're about to see, causes some pretty spectacular results. You know, making it sounds surprisingly simple. You just take some concentrated sulfuric acid and you add some potassium permanganate. The sulfuric acid is what's called a dehydrating agent. It's so thirsty for water that it literally rips water molecules out of the other chemicals. What you're left with is this very angry green oil, manganese heptoxide. So why all the drama? Well, its whole structure is just fundamentally unstable. It's like a tower of blocks that's about to topple over. It's just looking for an excuse, any excuse to decompose. A little bit of heat, or even just touching something else, is all the push it needs to violently break down into something more stable. All right, now for the really fun part. What actually happens when you introduce this self-destructing chemical to just everyday stuff? We're going to start with a few experiments using some simple solid fuels. First up, a totally normal cotton ball. For this experiment, there's a small pool of less concentrated manganese heptoxide in a dish. A cotton ball gets dropped in, and, well, the reaction speaks for itself. And that's the wild part, right? There's no fuse, no lighter, no spark. It's just contact. The manganese heptoxide acts as both the fuel source and the ignition all at once, and the cotton just instantly bursts into this really intense but very quick fire. Okay, next subject, a potato chip. It's the same idea, really. The oil in the chip acts as the fuel. But watch what happens here. See that huge puff of brown dust that gets thrown into the air? What is that? Yeah, that brown cloud is a byproduct called manganese dioxide. It comes out as this super fine dust that just hangs in the air. And let me be super clear here. This is the big takeaway. You do not want to breathe this stuff in. It is incredibly hazardous to your health. All right, now this is where things get a little strange. The next experiment used a more concentrated batch of the chemical. Now, common sense says that should mean a faster, even crazier reaction. But that's not what happened at all. And this is the real puzzle here. I mean, in chemistry, more concentration almost always means a faster reaction. You'd expect a bigger, quicker explosion, right? But instead, when they dropped a cotton ball into this purer stuff, it just sat there for a second. And then it erupted. Why the delay? So the best guess has to do with the leftovers. In the first, less concentrated batch, there was probably still some sulfuric acid mixed in, and that acid might have helped get the reaction going by attacking the cotton first. It seems the purest stuff is so volatile, it actually has a harder time initiating the reaction all by itself. And that little delay, it actually created a much more dangerous situation. It gave the fuel, the cotton, and the oxidizer time to mix together properly, creating a really sensitive explosive. So when it finally went off, it wasn't just a fire, it was a much more violent, explosive pop. So solids are clearly a bit unpredictable. But what about flammable liquids? This is where we get into something called hypergolic reactions, and this is a concept pulled straight from rocket science. A hypergolic combination is one of the coolest things in chemistry. It just means you have two liquids that the instant they touch each other, they ignite. No spark plug, no ignition system needed. You just mix them, and you get fire. It's a huge deal for rocket engines because it makes them way simpler and more reliable. So the experiments tried this with a few different liquids, like acetone, ethanol, and even an old-school rocket fuel called aniline. And every single time, it was the same story, an unbelievably fast and violent ignition. We're talking so fast, it only lasted for a few frames, even on a high-speed camera. And get this, the description of the ethanol reaction is just incredible. When they slowed the footage way, way down, the fireball it created apparently looked like a tiny mushroom cloud. Just think about that. That's the kind of instantaneous energy release we are dealing with here. So with all this incredible instant power and its hypergolic nature, you have to ask the question, could you use this stuff as rocket fuel? It seems like it has potential, right? But the reality, well, it's a lot more dangerous and complicated. I mean, just look at the pros and cons. The pro column is pretty short. It ignites on contact. That's it. The con column, though? Yikes. It's way too explosive to store safely. A decomposition reaction could travel right up the fuel line and blow up the tank. And then there's that brown dust again. It's just dead weight that doesn't provide any thrust and would probably clog the whole engine. And that's really the final nail in the coffin. The source puts it perfectly. It's just way too unpredictable, and the potential danger is absolutely not worth the risk. It's a fascinating chemical for sure, but it's not going to be powering rockets anytime soon. So we're left with this completely bizarre chemical that exists in a state of constant protest against its own existence. Its story is this incredible window into the extreme forces that are always at play on a molecular level. And it really makes you wonder, doesn't it? If something this unstable can exist, even for a moment, what other seemingly impossible materials are out there, just waiting to be made?